Hello and welcome everyone to today's webinar, which is brought to you by Bettersize Instruments in partnership with AZOM and AZO Network, and is titled Particle Size and Stability in Paints, Pigments and Coatings. A big thank you, as always, to the team at Bettersize for making this event possible, and to you and everyone in the audience for joining us from across the world. Before getting started, we have a few points about how to get the most out of the experience this afternoon. So firstly, the event is being recorded and we'll be sharing the on-demand link with you within the next 24 hours. So if you enjoy what you see, you missed anything or have a colleague or peer who might benefit from seeing the content as well, then please do share that recording with them when you get that email. Technical issues are normally resolved by refreshing your browser. However, if this doesn't work, send us a message using the Q&A box and our technical team will get you back up and running as quickly as possible. Today's webinar will run as 3 parts, 2 presentations and an audience Q&A session. We're delighted to be joined first by Dr. Beverly Barnum, Senior Application Scientist at Bettersize Instruments. Dr. Barnum received her Bachelor of Science degree in Chemistry from California State University and earned a PhD in Inorganic Chemistry from the University of Pennsylvania. She's recognized for innovative problem solving and is a highly accomplished scientist committed to advancing technological solutions. And joining Dr. Barnum is Weichen again. Weichen is an application scientist at Bettersize Instruments. He received his Bachelor's of Science degree in Material Science and Engineering from Harbin Institute of Technology and earned a Master's in Material Science and Engineering from the University of Florida. Since he joined Bettersize, Weichen has been focusing on the characterization of the physical properties of inorganic materials and helps provide relevant solutions. A big welcome to the two of you today. As I mentioned, there will be a Q&A session following the presentation, so please send those in as and when they come to mind using the Q&A box, which you can find on the right-hand side of your screen. Any we don't have time to get to today will be followed up via email at a later date. Right, I'm delighted to now hand things over to Dr. Barnum to get things started. Dr. Barnum, over to you.
Thank you for the kind introduction. Hello, everyone. Today I'm going to talk to you about inks, paints, and coatings. And I'll describe the importance of particle characterization and how to enhance and improve these materials through particle analysis. In the world of inks, paints, and coatings, the science of particle size and stability plays a pivotal role, influencing everything from color brilliance and texture to the durability and performance of the final product. Here's a quick overview of today's talk, with the objectives being to understand the basics of inks, paints, and coatings, explore the importance of their particle characteristics, learn how particle analysis optimizes these materials. Inks, paints, and coatings are widely used in various applications, such as printing, writing instruments, art, automotive, residential and commercial buildings, industrial machinery, protective and functional finishes, and specialty industries to enhance color, protection, and functional properties. Briefly, each class of materials has similarities and differences. Inks are paste or liquid substances primarily used in writing, printing, and drawing, comprised of a complex medium made of pigments, solvents, and other materials. Paints can be used for a variety of purposes, including artistic impression, residential and commercial decoration, and industrial applications. They're applied to surfaces to provide color, protection, and sometimes texture, comprised of mixtures of pigments suspended in a liquid medium, which is typically a combination of a binder, solvent, and additives. And coatings are similar to paints, but are often designed for specific functional purposes beyond just appearance. They can provide protective, decorative, or functional properties to a surface, and are comprised of pigments, binders, solvents, additives, and fillers. These can include varnishes, lacquers, enamels, and other specialized formulations in industries such as automotive, aerospace, and construction. So what do inks, paints, and coatings all have in common? They share the primary purpose of imparting color, protection, and specific functional properties to surfaces. They are comprised of similar fundamental components. Functionally, these materials rely on the effective dispersion of pigments to achieve uniform color and performance, and they often require stability to prevent settling, agglomeration, and other issues. Pigment is a material that exhibits a specific color because it selectively absorbs certain wavelengths of light. While many materials possess this property, pigments are stable at normal temperatures and have a high tinting strength. So only a small amount of it is needed to see the color when it's used on objects or mixed with a carrier. Many of the critical properties of inks, paints, and coatings, such as their color strength, covering ability, surface finish, and durability, are determined by the sizes and shapes of the dispersed pigment particles. So let's quickly review some definitions. What's a particle? Particle is a small unit of matter with defined physical properties such as mass, volume, and shape. Particles can widely vary in size and composition, ranging from subatomic particles like electrons and protons to larger particles like grains of sand. In the context of materials like inks, paints, and coatings, particles typically refer to the smaller solid components, such as pigments and fillers, that are dispersed within a liquid or solid medium to impart specific properties to the final product. And typical materials would include things like carbon black, titanium dioxide, organic and inorganic pigments. Now that we've defined what a particle is, here are some key particle parameters to consider. Particle size refers to a single value representing the measurement of the size of the diameter of an individual particle, while particle size distribution describes the proportion of particles to different sizes within a sample, not just the size of a single particle. This is often shown as a graphical representation. It provides information about the range, the ratio, and the distribution pattern of particle sizes across the sample. Particle size distribution plays a significant role in determining the performance and quality of inks, paints, and coatings. Particle shape refers to the geometric characteristics of individual particles, such as their form, roundness, and aspect ratio. These characteristics influence how particles interact with each other and their surrounding medium, affecting the performance and properties of these materials. Common particle shapes include spherical, plate-like, elongated, and irregular forms. Analyzing particle shape helps in understanding and optimizing various factors such as dispersion, stability, optical properties, and mechanical strength of the final product. Surface area refers to the total exposed outer surface of a particle or group of particles, essentially measuring the amount of surface available for interaction with other substances, and is directly related to particle size, meaning smaller particles have larger surface area per unit mass compared to larger particles. And this is often referred to as specific surface area. Porosity refers to the proportion of empty spaces or voids between particles within a material. It is a key factor in determining how well particles pack together, and it's directly related to the particle size distribution. Whereas density refers to the mass of a particle per unit volume. It is an important parameter that influences the behavior and performances of particles in various applications. And density can be classified into two types. There's true density, which is the mass of the particle divided by its actual volume, excluding any pores or voids within the particle. Bulk density is the mass collection of particles divided by the total volume they occupy, including the spaces between the particles. I want to focus on particle size and the corresponding particle size distribution and particle shape, and their role in influencing pigment dispersion. Smaller particles are better dispersed and able to disperse more uniformly. And this can lead to even coverage. Irregularly shaped particles have larger surface area, which can enhance dispersion and stability. However, this can also lead to increased viscosity and potential settle. If we move on to particle size influence on hiding power, opacity equals hiding power. So basically, it's covering ability. Smaller particles have a larger surface area to volume ratio, as I've mentioned, and this allows them to scatter light more effectively. This increased scattering enhances the hiding power of the coating, making it more effective at covering the surface. Particle size distribution With a well optimized distribution, you can get a mix of larger and smaller particles, and this can improve hiding power by maximizing light scatter and filling gaps in the coating. So, in summary, smaller particles generally enhance the hiding power of the coatings by scattering more light more effectively, while larger particles contribute less to the opacity. But optimizing the particle size distribution is key to achieving the desired level of hiding power within these materials of inks, paints, and coatings. Moving on to the size and shape effects on the optical properties. Two phenomena govern both hiding power and the color strength of inks, paints, and coatings. Light absorption and light scattering of the pigment particles that are within the material. Color strength refers to the intensity of color a pigment can impart to a material, which is directly related to the size of its particles. Well-dispersed fine particles provide better color consistency and hiding power, resulting in vibrant color appearance, compared to larger, poorly dispersed particles, which tend to scatter light less effectively, resulting in a weaker color strength, leading to a more muted or dull appearance. Particle shape, where spherical particles can provide a smooth and uniform dispersion, which helps in achieving consistent color strength. Irregular shaped particles can scatter light in multiple directions, which can actually enhance the color strength. So, an ideal distribution is a well-balanced distribution of particle size and shapes, which can enhance color strength by maximizing light absorption and scattering and result in more vibrant and intense colors. Particle size analyzers like laser diffraction can be used to measure the particle size distribution of a pigment, which can then be correlated to its color strength. Particle size and shape impact other characteristics of these materials. There's viscosity, where smaller particles have in their higher surface area increase the viscosity of the formulation, which affects the ease of application and leveling. However, irregular shapes can increase interactions with the surrounding fluid, and this can also lead to higher viscosity. In terms of mechanical properties, smaller particles enhance smoothness and durability. However, irregular shapes can improve mechanical interlocking, enhancing properties like adhesion and scratch resistance. In terms of durability, smaller particles fill voids effectively, creating denser and more durable materials. But irregular shapes can enhance wear resistance and withstand mechanical stresses. And in terms of weathering, smaller particles provide better coverage and protection against environmental factors. However, irregular shapes can enhance protection against moisture and UV radiation. In summary, both particle size and shape are critical factors that influence the dispersion, stability, hiding power, mechanical properties, and final appearance of inks, paints, and coatings. Proper optimization of these factors is essential for achieving high performance formulations. So next, I want to discuss the importance of stability and zeta potential. And of course, what is zeta potential? Zeta potential is not a property of the particle, the system, comprised of the particle and the dispersion medium. Zeta potential is a measure of the electrical potential at the slipping plane of the particle in the medium. It indicates the degree of electrostatic repulsion or attraction between the particles. High zeta potential means strong repulsion between particles, like common magnetic poles, which help prevent agglomeration and ensures stable dispersion. It's a critical parameter for understanding and controlling the stability of colloidal suspensions, such as those found in inks, paints, and coatings. There are many factors that affect zeta potential, including pH of the suspension, the ionic strength of the solution, the type of electrolyte ions, the temperature, which can affect the viscosity and dielectric constant of the medium, as well as the diffusion and mobility of the ions in the suspension. Particle concentration can lead to particle-particle interactions, which can affect the overall zeta potential. Presence of surfactants, polymers, solvent properties, And surface modification of the particle with coating or functionalization can alter the surface charge and thus the zeta potential. So what is the importance of zeta potential? Having high zeta potential controls particle stability. High zeta potential, either positive or negative, creates strong electrostatic repulsion between the particles. This repulsion avoids clumping and aggregation and prevents particles from coming together, forming stable suspension. Maintaining the high zeta potential ensures that particles remain evenly dispersed in the medium, preventing them from settling. It maintains that uniformity. Electrostatic stability involves maintaining the forces that keep the particles apart, and this will prevent them from settling at the bottom of the container. By adjusting pH and conductivity, manufacturers can achieve the optimal zeta potential for stable dispersions. Using dispersing agents such as surfactants and stabilizers can add to formulations to improve the electrostatic or steric repulsion between the forces, and this further enhances stability and prevents aggregation. By ensuring consistent and reliable formulations, it's dependent upon preventing settling, agglomeration, and flocculation. So manufacturers can ensure that they don't settle, aggregate, or flocculate, and maintain the properties throughout storage and application. Proper control of zeta potential and stability ensures that each batch of product has the same uniformity, performance, and quality, minimizing variations and defects. So developing high quality inks, paints, and coatings involves navigating a range of formulation and processing challenges. Understanding and addressing these issues with targeted solutions ensures optimal performance and consistency across applications. Common formulation challenges include achieving consistent particle size distribution. Here, the challenges involve smaller particles which may aggregate, forming large clusters that affect performance. Part of the solutions involve using advanced particle size analyzers to monitor and control particle size distribution, and employing dispersion techniques to break up aggregates and ensure uniform particle size. In terms of balancing stability and performance, the challenge is when environmental factors such as temperature and humidity can affect the stability and performance. By conducting stability testing under various conditions, you can identify the optimal formulations and use stabilizers and performance enhancers that are compatible and synergistic. In terms of processing issues, the goal is to prevent sedimentation and caking. This will ensure long shelf life and uniform application. Because the challenge is that particles can settle over time, leading to a separation of the components. And high viscosity formulations may be prone to caking, forming hard lumps, and are difficult to redisperse. So solutions include using thickeners and stabilizers to maintain the suspension and prevent sedimentation. Controlling viscosity ensures a smooth flowing consistency, and optimizing storage conditions such as temperature and humidity to reduce the risk of caking. Another processing challenge is to ensure uniform mixing. It's important that we achieve consistent formulation and application processes to know that all components are evenly distributed. Inefficient mixing can lead to uneven distribution of the pigments, binders, and additives, and this will affect color and performance. This is especially important in large batches, as this may present difficulties in achieving thorough mixing. Solutions include mechanical mixers to break up the clumps and ensure even distribution. Using real-time monitoring techniques to assess mixing efficiency is important, and you can adjust the parameters as needed. In terms of quality control, the goal here is to maintain batch-to-batch consistency to ensure product reliability, customer satisfaction. Challenges, of course, arise from the variability in raw materials and process conditions, which can lead to differences in color, viscosity, and performance. Solutions include implementing strict quality control measures, including incoming raw material inspection and testing, developing and adhering to SOPs for production processes, and performing regular calibration and maintenance of equipment to ensure accuracy and reliability. If we address environmental factors in order to maintain product performance under varying conditions, which include temperature, humidity, and exposure to light. The environmental factors and cause degradation of pigments, binders, and additives, which lead to changes in color, stability, and performance. Solutions include conducting environmental testing to assess the impact of these different conditions on the product stability and performance, and as a result, use robust formulation additives that are resistant to these environmental factors, and optimizing package to protect the products from external influences. A solution to address the challenges in formulations and in quality control is to employ advanced characterization techniques. This provides detailed insights into particle properties and formulation performance, enabling precise control and optimization. Examples include laser diffraction, which measures particle size distribution, ensuring uniformity and consistency. Dynamic light scattering analyzes particle size and distribution in colloidal systems. Zeta potential measurement assesses the electrostatic stability of particles, preventing aggregation. Rheology analysis evaluates the flow behavior of formulations, optimizing viscosity and application properties. Electron microscopy provides information on particle size, morphology, and surface topography. Static multiple light scattering characterizes the stability of dispersions. Image analysis provides particle size, shape, and distribution information. And BET, Bronauer, Emmett, Teller provides information about the particle size, porosity of a material. Solutions to common challenges include optimizing formulation parameters. The importance of this is that it enhances product performance and consistency by fine-tuning the composition and processing condition. One example would be to adjust the pH, which we have mentioned ensures optimal zeta potential and resulting stability. And this prevents issues like agglomeration and sedimentation. By selecting the appropriate stabilizers, this can enhance the dispersion and prevent the aggregation. And fine-tuning the additive concentrations will balance performance and stability without compromising either aspect. So ensuring the right balance of these additives to achieve desired properties will add to the durability, gloss, and adhesion of these materials. So as we wrap up part one, let's highlight the critical aspects that impact the performance and quality of inks, paints, and coatings. The importance of particle size and shape, the role of zeta potential and stability, and the common challenges and solutions in formulation and quality control. And I hope that I've helped you understand the whys of the importance of particle characterization, how to enhance and improve these products through particle analysis. Now I'll hand this over to my partner, Weichen, to explain how you can use particle size distribution, zeta potential, and stability analysis with some interesting case studies in part two of this presentation.
Thank you, Danny, and thank you, Beverly, for your comprehensive introduction. Hello, everyone. I'm Weichen, an application scientist from Bettersize. As my colleague Dr. Barnum laid the theoretical groundwork for optimizing inks, paints, and coatings, now we will explore the how we measure and control key parameters like particle size. Through 3 case studies, I will demonstrate practical measurement techniques and their impact on efficiency, quality, and performance. Let's dive in. Let me briefly introduce the 3 case studies we will be examining. First, we will explore the critical relationship between particle size and spray paint quality. Following that, we will discuss the significant role of zeta potential in ink evaluation. Finally, we will delve into a robust method for qualitatively analyzing coating stability. I trust that these practical examples will provide valuable insights into optimizing your own processes. This is our first case study, monitoring spray paint quality with the Bettersize 2600. Why is my spray paint not working is a question many of us have asked. We listed out some common culprits here, everything from low pressure and poor mixing to clogged nozzles and improper storage. But what's often overlooked is the critical role of particle size. Even if all these other factors are adjusted, inconsistent particle size distribution can lead to a host of problems: uneven coverage, poor finish, color inconsistencies, and of course, premature clogging we are going to see in the following discussion. In this real-world case from a leading paint provider, the nozzles of canned paint clogged abnormally often. The culprit was identified using the Bettersize 2600 oversized particles. This distribution curve reveals of those oversized particles that peak highlighted with the red box, even when most particles are in the right size. These oversized particles can disrupt the optimal packing of smaller particles, reducing overall viscosity and leading to inconsistent flow and clogging. The animation on the right shows how agglomerates clog nozzles, leading to spray paint failure. The Bettersize 2600 helped this paint provider identify and quantify these oversized particles, allowing them to adjust their process and solve the problem with an optimized grinding setup and finer filtration. Now, let's talk about the Bettersize 2600 laser diffraction particle size analyzer itself. Its tagline, "Better particle sizing for every need," really sums it up. This award-winning instrument, recognized with the 2024 iNovo Award, offers unparalleled measurement capabilities with its modular design, from paint suspensions to pigment dry powders. With its unique optical design, the Bettersize 2600 boasts an exceptionally wide particle size range, handling everything from 0.02 to 2,600 microns with wet dispersion and 0.1 to 2,600 microns with dry dispersion. Beyond size, the Bettersize 2600 also measures particle shape, another crucial factor thanks to the powerful Pig-1 image analysis module. For even larger particles, its dynamic imaging capability covers 2 to 3,500 microns. This versatility is achieved through its unique combination of laser diffraction for rapid size analysis and dynamic imaging for detailed shape information. As a summary, let's talk about how can we measure particle size to optimize quality inspection. Traditional methods like sieving and filtering have long been an important part of paint production processes. Sieving physically separates particles, which is essential. However, it presents some challenges, especially when dealing with fine particles around 40 microns and below due to issues like mesh size limitations and particle agglomeration. It can be difficult to handle these fine materials effectively, and the resolution and accuracy of sieving can be limited. While sieving provides a systematic and reliable process, the results themselves can lack the precision needed for modern formulations. That's where the Bettersize 2600 comes in. This advanced particle size analyzer allows us to precisely measure and control particle size distribution, ensuring consistent spray paint quality and minimize those frustrating issues. Like sieving, it ensures a systematic and reliable testing process. But unlike sieving, it delivers dependable results with detailed statistics from a large number of particles. This allows for more precise quality control and optimization of your paint formulations. we have seen how the Bettersize 2600 revolutionizes particle size analysis in spray paints. Let's move on to our second case study, evaluating ink quality with a zeta potential test of the Binano series. Our second case study focuses on inks and the critical role of zeta potential. As the subtitle suggests, we are investigating nano-sized pigment dispersibility and stability in inks, a core challenge in ink formulation. A stable dispersion brings several key benefits. It prevents clogging, ensures consistent color output, maintains the correct ink viscosity, improves print resolution, and even extends shelf life. This image on our right illustrates some common consequences of unstable dispersions: sedimentation, viscosity changes, and flocculation. In the following discussion, we will see how the Binano instrument helps us understand the suspension stability to achieve optimal ink performance. Understanding suspension stability hinges on zeta potential. As mentioned by my colleague Dr. Barnum, the image on the right explains what zeta potential is, the electrokinetic potential at the outer layer of a particle. The zeta potential affects the concentration of charges around the particle, thus affecting the charge stabilization effect. This chart on the left, based on empirical observations, demonstrates the direct impact of zeta potential on suspension stability, revealing the following change. As the absolute value of zeta potential increases, the suspension system becomes more stable due to charge stabilization. However, please note that the value listed here serve as general guidelines, not absolute thresholds. The B-nano provides reliable zeta potential analysis, crucial for keeping pigment stability dispersed in inks. Here, we have a phase plot on the upper right and corresponding results down here from a nanopigment ink sample. This sample is a complex mix of nano-sized pigments. The measured zeta potential of around 30 millivolts shows Binano's precision even with complex ink formulations. Knowing the zeta potential let us targeted adjustments for ink stability. We can make the adjustment in several ways. For example, in water-based inks, we can change the environment's pH by adding acids or bases, which alters the surface charge of the pigment particles. Or we can also change the ionic strength by adding salts. This affects the double layer around the particles. Here is the start of our show for ink analysis, the B-nano nanoparticle size and zeta potential analyzer, striving to be the nanoparticle expert you need. This powerful instrument is designed for precision and versatility. For zeta potential measurement we have discussed, even samples with low electrophoretic mobility, which can be particularly challenging, are no problem, thanks to its pulse technology. For comprehensive zeta potential analysis across a wide pH range, the BAT1 auto-titrator is seamlessly integrated. It also measures the size of nano-sized samples down to an incredible 0.3 nanometers, covering a wide range of particle sizes. Its wide concentration range up to 40% is made possible by its DLS backscattering technology. Finally, let's turn our attention to our third and final case study, analyzing the stability of coatings. Just like Dr. Barnum mentioned in the first part, stable dispersion systems rely on a combination of factors, not just one. We have already discussed the crucial role of zeta potential in the last case, but other key factors come into play. These include steric hindrance, particle size, density, viscosity, pH range, and temperature. A truly stable coating requires careful optimization of all these interacting parameters. How do we analyze the stability of coatings and other suspension systems in general? Static multiple light scattering, or SMLS, is a powerful, non-destructive, simple, and fast technique. As you can see, SMLS shines a light source on the sample, and the test resulting light is collected by detectors. The whole optical system scans across the sample, collecting resulting optical signal data over time. Usually, an SMLS instrument provides both transmitting and backscattering optical signal data. Because coatings are typically opaque, transmitted light signals are often weak, making backscatter light a more reliable indicator of changes within the sample. Therefore, backscatter light are preferred for the SMLS analysis of coatings. The signal collected by the SMLS instrument is recorded into two forms: raw data and delta data. Raw data represents the original unprocessed signal detected by the forward or backward detectors. It's the baseline we use for comparison. The delta data, on the other hand, tells us about change. It's calculated by differencing subsequent scans from a reference scan, which is typically the very first scan. The delta data provides a quantitative method to understand how the sample structure evolves over time. For example, here we show an ideal sedimentation backscattered raw and delta data. The delta data exhibits a characteristic pattern. Backscatter light is getting stronger at the bottom of the bottle and vice versa at the top. That indicates particle concentration on the top is reducing and at the bottom it is growing, which means particles are migrating from the top to the bottom. Yes, that indicates sedimentation. But how do we quantify stability? We use the instability index. The instability index is calculated by accumulating the differences between a successive scan and a previous scan. These differences are then mathematically combined into a single value that represents the stability for the whole sample at one corresponding scan. If one scan has a lower IUS value, say 0.5, it indicates that at this moment the system is in a stable status. On the contrary, if the IUS value is larger than 10, you may be witnessing an obviously unstable phenomenon like sedimentation, flocculation, or delamination. Now, let's look at the instability index versus time curve for our titanium oxide coating samples. As you can see, the sample with 1% span 80 curve rises rapidly, indicating a significant increases in instability over time. In contrast, the 1% SDS sample exhibits a relatively flat curve and low IUS value, suggesting that its stability remains consistently high throughout the 1 hour plus period. The instability index provides an elaborate view of stability, capturing both discrete snapshots of stability at specific moments and revealing the dynamic evolution of the system over time. Thus, we can make informed decisions about formulation optimization. However, while the instability index provides a convenient and quantitative way to access its overall stability, it's important to remember that it doesn't tell the whole story. It gives us numbers and curves, but it doesn't specify how the system is destabilizing, whether through sedimentation, agglomeration, or some else mechanisms. For that level of detail, we need to return to the delta data. To wrap up this section of coating stability, let me introduce the B-Scan Lab Stability Analyzer. Based on SMLS technology, The B-Scan lab provides quick and direct stability measurements, capturing subtle variations far faster than the human eye. It offers both qualitative and quantitative stability results, recognizing a range of unstable phenomena and allowing you to study destabilization kinetics. This analyzer can handle a wide range of samples, including films, suspensions, and emulsions, even at high concentration up to 95 per volume fraction like paints or inks. And because it's non-destructive, non-contact, and require no diluting or sharing, it preserves sample integrity. With its one-to-many system, you can connect multiple B-Scan lab units, saving valuable time by measuring multiple samples simultaneously. To summarize our exploration of particle characterization, let's consider how to choose the right tool for the job. Both electrophoretic light scattering, the ELS, and static multiple light scattering, the SMLS, offer valuable insights, but they are best suited for different applications. Choose the SMLS when you need a comprehensive evaluation of stability, including both qualitative and quantitative analysis. It is also worth noting that the SMLS provides quantitative view of stability dynamics, revealing how quickly a system changes over time and providing insights for optimizing formulations and ensures product quality. SMLS is ideal when you have sufficient sample volume, typically 4 to 25 milliliters, and when dealing with high viscosity and highly concentrated samples. On the other hand, the ELS is preferred choice when you focus on the electrostatic stabilization. It's perfect for rapid stability evaluations, often requiring less than a minute. ELS is also essential when working with limited sample sizes as it only needs 0.75 to 1.5 milliliters. And remember, ELS testing can also provide valuable information about particle size distribution through a DLS test. By carefully considering these factors, you can select the optimal technique for your specific needs, ensuring the best possible quality for your products. These are just a few of many success stories we have seen with Bettersize products. Leading brands in the paint, ink, and coating industries rely on Bettersizer products for their particle characterization needs, from optimizing ink formulations for vibrant packaging, just like the case study we saw earlier, to ensuring the precise particle size for critical pigments in coatings. And the list continues to grow. We are proud to partner with companies that are pushing the boundaries of innovation, and we are committed to providing them with the tools they need to succeed. Let's recap what we have covered today. We began by understanding the critical role of particle size in spray paint quality and how the Bettersizer 2600 helps manufacturers identify and control oversized particles to prevent nozzle clogging, thus ensure consistent product. We then explored the importance of zeta potential in ink stability and how the binano instrument helps control the crucial parameter, leading to optimized ink formulation with the superior color consistency and shelf life. Finally, we delve into the world of coating stability, demonstrating how static multiple light scattering and the B-Scan lab analyzer provide both qualitative and quantitative insights into destabilization mechanisms, allowing for rapid and effective coating formulation development. From optimizing practice size in spray paints to ensuring ink stability and analyzing complex coatings, Bettersize offers a comprehensive suite of solutions for particle characterization. Thank you for your attention and engagement throughout this presentation. I hope you find the information valuable and that it sparks new ideas for optimizing your own products and processes. My colleague Dr. Barnum and I welcome every question you may have. We look forward to further discussion in the Q&A section. Thank you.
All right, so superb stuff, Weichen. Superb stuff, Beverly. We're now going to move into the Q&A part of the webinar. We're just going to bring our two fantastic speakers back on. And just before we do that, we have got a few announcements to run through. First of all, if you're interested in a free sample testing, then you can click the link that should be appearing on your screen right now. I'll leave that up for a few moments and you can click on that and it'll take you to a page where you can find out more information about that. And another very exciting bit of news is that this year, Bettersize is celebrating its 30th anniversary and has extended the warranties to 3 years for all of their analyzers. So if you're interested in any of that, then you can contact the team. The details on the screen there, email address ready to contact them. Okay, let's get things started with the Q&A. And Weichen, I'm going to come to you first for this first question. This one's asking, can you translate and correlate the results to other analysis techniques like Hegman grind?
Yes, thank you, Danny. So the PSD, I mean, the particle size distribution from laser diffraction is just absolute intensities transformed into size. So categorizing into other formats like the particle classification like a sieving can be done. The software of a particle size analyzer, such as our Bettersizers software allows the end user to define particle size classification and doing sieving simulations and percentile value settings, so as well as create customized reports. Talking about the specific analysis techniques like sieving or screening we have covered in this speech, it would be easy to transform since the results are provided in weight content, which can be easily translated into volume distribution from laser diffraction. And when talking about the Hegman grind or Hegman gauge, it is surely an easy and cost-effective way to verify oversized particles in the ground pigments in paints. However, laser diffraction can do the same thing in a similar time efficiency and provide particle size distribution, which shows the accurate content of particles at a specific size, as we showed in case 1 of the part 2 speech, which is my part. Think about what we can do with a high resolution PSD curve. You will know improving pigment processing can never be so precise. And for additional information, such as a sieving simulation report or customized size classification report, you can feel free to contact Bettersize support. We are happy to assist. Thank you.
Superb. Beverly, and I'll bring you in for this next one. It's number 2 on our list. It's asking, can size analysis be used for real-time or near real-time QA, or is it primarily a development tool?
But it depends in terms of real-time or near real-time QA. Depends on how you implement particle size analysis into your process. We could set a particle sizer into the processing line, and that's called online particle sizing. Then that's obviously a real-time quality test. But oftentimes, more practically, we pick out samples from the processing line and then test it. And this is we're able to do this because most sizing tests take only minutes. And so this is called inline testing. And the inline testing works as an efficient QA tool, but it's not real time, obviously, because it's not within the system. But compared with other techniques, this works very well. The last thing to be careful, of course, as always, including research and in production, is in terms of gathering your sample and making sure you have proper mix, what we call riffling the samples and things like that.
Fantastic. And there's a quick follow-up to that one as well. It's asking about the time required. So what is the time required for analysis?
Well, as I suggested, generally for particle size analysis, the test only takes minutes. This would include multiple repeats in order to ascertain the consistency and reliability and repeatability of the data. For things like zeta potential and size, for sedimentation studies, typically studies start at an hour, maybe even as short as 20 minutes, but you have the capability to run for hours, days, and even weeks for those kinds of studies. And that is obviously related to the data you want to acquire.
Fantastic. Weichen, I'll bring you back in. Question for analysts. Are there limitations on the particle chemistry? Can you do both organic and inorganic pigments?
Well, yes. So it really depends, since there are some extremes or limitations, but generally speaking, like our organic or inorganic pigments can be both easily analyzed. Like if you select a proper medium to dilute or to send to dilute the sample, to disperse them for wet dispersion, which can be used in both laser diffraction, we discussed in the dynamic light scattering, for the Binano series, and the SMLS test. They all can do it in both organic and inorganic way. Or you can use some of dry powders, for example, some pigments, or grind it. For laser diffraction, it is also possible. Thank you.
Perfect. Beverly, what about this? Can you analyze the samples as is, or are you required to dilute or treat the sample? And also how to handle the agglomeration or / de-agglomeration?
Generally, some dilution is needed to avoid multi-scattering. But as my partner Wei Cheng-Gan had mentioned, SMLS, you can use almost 95% volume dispersion, so very little just medium for dilution. Agglomerations are typically handled in many of our devices, for example, in laser diffraction with mechanical stirring and adjustable ultrasound. And obviously you can prepare your sample externally with an external ultrasound. And again, we can use the addition of surfactants and dispersing agents to help in terms of how to handle agglomeration and de-agglomerations. So those are some of the solutions that we offer.
Fantastic. Weichen, what about number 8? Can the paint particle be in atomic level?
Well, yeah, so this is a very interesting question. So at the very first beginning, I would say like paint particles cannot be at the atomic level. So here is why. When we considering the paint composition, thinking paint is a complex mixture. It is primarily composed of like pigments, binders, solvents, and some else additives. Think about the pigment itself. They are typically in the range like from say zero point 0.1 to 10 micrometers, or we say in the microns. So if we can put that into perspective, 1 micrometer or 1 micron equals to 1,000 of nanometers, and 1 nanometer equals to 10 angstroms. So for the atoms, like they are in order of like 0.1 to 0.5 nanometers, which is 1 to 5 angstroms in diameter. So therefore, a single pigment particle is like thousands of tens of thousands of times larger than a single atom. So pigment particles are aggregates of many, many molecules, and those molecules are in turn made up of many atoms. Such things also happens with binders and solvents. So if the paint particles were individual atoms, you actually won't be able to see them, even with a standard microscope, the optical microscopes. and the paint would be transparent in return. Pigments need to be much larger than atoms to interact with the light waves in a way that produces color. And so, in summary, the paint particles are much larger than individual atoms. They are actually in molecular scale, something like that. So, yeah, I hope that helps. Thank you.
Fantastic. We've got plenty of questions. There's going to be some questions left unanswered today. We'll send them over to the team at Bettersize to follow up via email if we don't get a chance to cover it. There's a few dozen at the moment, so we'll get through as many as we can. Just a quick note that there are some handouts on the left-hand side of your screen that you can download and take away with you before the webinar finishes. So please do download those before you finish up today. Okay, let's go to number 10 on our list, Weichen. So what particle size is considered small in this context?
So I think that is one question that relates with the last one. So we are, as we have experienced, so usually the pigment particles in the range of 0.01 to 10 micrometers, usually they are more going to the 0.01 side, just like what we showed in the part 2, which is my part, that there is some particles that D10, which means like 10% of particles are around like 0.01 something, and 90% of particles are smaller than 0.02. So you can see that this is a very small scale. Particles that like smaller than 100 nanometer, which is equals to 0.1 micrometers, that can be considered as small in the pigment side. Thank you.
Okay, Beverly, we'll bring you back in for this question 15 on our list. Is there a correlation between actual size and the D50 value obtained in DLS technique?
So although D10 and D50 and D90 can be obtained through DLS, it's not commonly the standard used for particle size nanoscale. So generally, in terms of dynamic light scattering, we use the reference of the average particle size as a quantitative perspective, as it's more repeatable than other size distribution results. So the Z average, the dispersity index, and the intensity distributions are the most authentic size results calculated from the correlation function that is achieved through dynamic light scattering. And these results are what's most used in DLS applications and industry standards. And again,
All right.
as we mentioned, yeah, D10 is like 10%, D50 is 50%, and D90 is 90% of the particle sizes are of that number. Thanks.
Superb. Let's try and take a couple more. We're getting fairly close to the hour, but let's go down to number 18 on our list. Up to what particle size does the Bettersize 2600 measure?
Yeah, well, so this would be a very easy question, since namely the upper size limit of Bettersize 2600 is 2600 microns. But one thing worth noting that if we connect a Bettersize 2600, combine it with a PIC1 image analysis module, the upper limit would be 3,500 microns. So this is it.
Fantastic. We'll just take one more. I've just put the free sample testing link back up on the screen, so please do click on that before you leave the room, before you leave the webinar if you're interested. And don't forget to download the handouts, which you can find on the left-hand side of your screen. Final question for you, Weichen. How does the particle size affect the instability index?
Well, this is a very good one. So actually, it was kind of complex, but let us put everything long in short. So if the particle size are changing in somehow, it will make the instability index larger. So if the particles are growing like they are agglomerating or flocculating, the system, I mean the suspension system would be unstable. Thus, it will cause a larger instability index. But on contrast, if the particles are getting smaller, like the particles are splitting, it is actually they are happening something like the system is not so stable also. So the instability index will also grow. So the best situation for everyone is the particles stay in a stable size and they are stably dispersed in the system. So the instability index will keep low. I hope that helps.
Fantastic. Well, we'll finish things up there. Final reminders to everyone in the audience that you can download the handouts. You'll be getting an email over the next couple of days with a link to all the resources and to the recording that will come from the team at Bettersize. So be on the lookout for that. Final reminder also about the 30th anniversary. If you are interested in any of the analyzers, there is a 3-year extended warranty this year. So be sure to contact the team to find out more about that. We will wrap it up there. I'll leave the webinar open for a couple more moments. So if anyone has any final questions, they can put it into the Q&A box. All of them will be handed over to Beverly and Weichen to follow up with as and when it's possible. So thank you to the both of you. And thank you to everyone in the audience for tuning in from across the world. Wish everyone a pleasant rest of the day and hopefully see you all again very soon. Take care.